This video introduces a classification-based approach for approximate reachability. Hamilton-Jacobi reachability analysis aims to verify goal satisfaction and safety for general nonlinear dynamical systems. We will denote as C the trajectories of this system, which evolve according to the initial state S, initial time t, and the control and disturbance signals U and D. For goal satisfaction verification, we define a target set L as the zero-sub-level set of a signed distance function. We keep track of the trajectories of this cost functional, which ensures that trajectories that enter the target set are assigned a negative cost, while trajectories that do not enter the target set are assigned a positive cost. Reachability theory also applies to safety verification. Here we illustrate two circular obstacles in the state space that we would also like the system to avoid. Like the target set, these constraints are also defined by the zero-sub-level set of a signed distance function. A slightly more complicated reachability cost functional assigns negative cost only to those trajectories that reach the target set without violating a constraint. For example, one of the trajectories is assigned a negative cost because it reached the target set without violating a constraint, while the other one is assigned a positive cost. Note that this framework also applies to time-varying target sets and time-varying constraint sets. Equipped with these formalisms, we can define the value of a state when control and disturbance play optimally. This value function is the minimum attainable cost if the disturbance plays adversarially. Traditionally, solving for this value function involves discretizing the state space and solving a large dynamic program. While this strategy can yield very precise results, its complexity scales exponentially with state dimension. Grid-based approaches are generally not tractable in dimensions greater than 5. There are some other strategies with improved scaling properties. Unfortunately, they often make restrictive assumptions on system dynamics, safety constraints, and set geometries. In this paper, we propose a new method for computing approximately optimal control and disturbance policies for a broad class of dynamical systems in which control and disturbance enter linearly. We show that, at each step, the optimal control and disturbance policies for these control-affine systems may be represented as a set of binary classifiers. We learn a sequence of time-indexed binary classifiers for both the control and if needed the disturbance. Let's assume there is no disturbance, and that we already have control policies for the first two time steps. We proceed by sampling points uniformly at random from the state space. Since the dynamics are control-affine, we can compute the optimum for a specific state by swapping one element of the control vector at a time, and using the stored policies to simulate the remainder of the trajectory. We repeat this computation for each sample state. Finally, we accumulate these optimal controls into a large dataset which we use to train binary classifiers for each control component. Replacing the optimal control with a set of learned binary classifiers results in an increased cost at every state. This means that the level set of the value function induced by our controller is a subset of the same level set of the original value function. We also repeat these experiments for another 2D system and another 4D system. Finally, we also apply this technique, including disturbances, to the recent fast-track framework for fast and safe dynamic motion planning. Here, we demonstrate our learned controller on a Crazy Flight 2.0 in a motion capture room. As seen in the video, our controller remains within the computed tracking error bound.